today's session, I'm going to deal with. I'm going to discuss about the stresses in uniformly tapering bars, tapering sections. Okay. As a first case, let us discuss about uniformly tapering section of circular cross section. Circular cross section with the diameter capital D at one end and small d at the other end, and L being the length of the bar. L being the length of the bar. So for this section, under the axial load W, what will be the elongation of the section? The stresses here are not uniform, okay? Because the cross-sectional area reduces or changes from one end to the other end. Because the diameter is uniformly varying, the area also changes, and hence the stress. Okay? So the stress is not constant, and to find elongation of such a bar, we consider initially an elementary strip at a distance x, at a distance x, and we are taking the origin at A, which is the point of intersection of these slant edges. Okay, it is a conical section actually, with diameter small d at one end and capital D at the other end. So on the extension of these slant edges, the point where they both intersect is the point A, and the distance of this point A from the small diameter is L naught. Okay, so here the projected shape of this bar is seen as a trapezium actually. Okay, the projected shape of the bar is seen as a trapezium. Uh, so here, to find the radius of cross section at any distance x, we will make use of the properties of similar triangles. Properties of similar triangles. So the triangles are said to be similar when the angles are equal. Okay, the two triangles are said to be similar if the angles, corresponding angles, say alpha, beta, and gamma. If the angles here also are alpha, beta, and gamma, then they are said to be similar. And one property of such triangles is the ratio of corresponding sides. For example, if it is A, B, C, A1, B1, C1, the corresponding edges are here AB and A1, B1. These two edges are corresponding edges. Similarly, BC corresponds to B1, C1, and AC corresponds to A1, C1. So the ratio of corresponding sides is equal. That is, BC by B1, C1 is equal to AC by A1, C1 is equal to AB by A1, B1. Okay. So these ratios of corresponding sides are equal. That is one property of similar triangles. So by making use of this, we will find the radius r of the cross section at any distance x. Okay. So here, uh, for this purpose, we consider uh, the triangle. Let us consider this. Yeah, this one actually. So this length is small d by 2, and this is also small d. And this is smaller radius, this is capital D by 2. Half of the diameter. And this is extension, this is point A, as shown before. Okay, this figure. So here the radius R, and how about this distance? X. And this distance L0, and this is L. Okay, let us call this as A, B, B1, and this is C, C1. Okay, so the ratio of corresponding sides is same, huh? Isn't it? So here this is also R radius. Okay, so by using this property, first we will find the relation between L0 and L. We can find that. Okay, for that we consider the ratio of AC, this horizontal edge, by BC is equal to AC1 by B1 C1. Okay, AC1 by B1 C1, corresponding edges. So AC is here L0, and BC is small d by 2, and AC1 is L plus L0 and capital D by 2. So L0 into D by 2, DL0 by 2 is equal to small d L by 2 plus small d L0 by. So 2 cancels here, and bringing this L0 to the left hand side, you will have L0 into capital D minus small d is equal to DL, or L0 is DL by capital D minus small d. So this is the relation between L0 and L. Okay. Yeah. Now we find the radius R. The corresponding sides here, we consider this triangle ABC and this triangle. Okay, in which the sides, corresponding sides are AC by BC is equal to X by R. X by R. Okay, so and X by R is equal to AC is L0 by BC is D by 2, and L0 is DL by this way. We substitute this DL by capital D minus small d into 2 by D. Okay, so small d cancels here. We will have R is equal to D capital D minus small d by 2L into X. Okay, so this is the radius of n section at a distance X from uh, point A here in this figure with reference to this figure. Okay, so this is the radius of section. So all these sections are subjected to a load of W, axial load of W. The bar is subjected. Okay, so we consider the elementary strip of width dx or length dx. You call it. This length is dx. Okay, and area of cross section at a distance x is pi r square. Okay, So the stress sigma at a distance x, that means the on the cross section with radius r, the stress on this section is W by area pi r square. So the stress on the elementary strip is W by pi r square, W by pi r square, and where r is r, we know that capital D minus small d by 2l into x. Okay, so substituting this here, W by pi into small capital D minus small d whole square x square, and in the numerator we will have 4l square, 2l, so 4l square. So stress on the elementary strip is 4wl square by pi into capital D minus small d square into x square. Okay, and the length of the bar is dx. Okay, so the strain of the element is given as extension of the element by length actually, which is also given as stress by Young's modulus. Okay, stress by Young's modulus, and this strain is given as extension of element divided by length of element dx. Okay, so extension of element, let us represent that by delta x by dx. This is the length, dx is the length, is sigma x by e, and sigma x is given by this. So 4wl square by pi e into d minus d whole square into x square. Okay, or delta x is equal to the extension of elementary strip is 4wl square by pi e into d minus d square into x square into dx. So this is the extension of elementary strip, and the total extension of the rod, tapering rod, is obtained by integrating this between the limits of x. And here x varies from L0 to L0 plus L. The limits of x are L0 to, the limits of x, L0 to L plus L0. Okay, so they are the limits of x. So by integrating this, you will get the total extension of the tapering rod. Okay, total extension of the tapering rod. If it is of uniform bar, then we can directly find the total extension as PL by AE. PL by AE. But here, as the cross section is varying, the stress also varies, and the extension is to be calculated by integration. Okay, so the integration of this is the total extension delta of the tapering rod is taking the constants out, 4wl square by pi e into capital D minus small d whole square into integral 1 by x square dx. Okay, 1 by x square dx. So this is all constant. We can take that out. So you'll have 1 by x square dx. and the integral of which is minus 1 by x. Integral of which is minus 1 by x between the limits L0 to L plus L0. Okay, so this is 4WL square by pi e into d minus d whole square. Integral of 1 by x square is minus 1 by x between the limits L0 to L plus L0. So we have already calculated what is L0. What is L0 here? dl, small dl by capital D minus small d. Similarly, we will find L plus L0, L plus L0 as L plus L0 is dl by capital D minus small d. Okay, so this becomes dl minus small dl plus small dl divided by d minus d, or dl and dl cancels. You will have capital dl by capital D minus small d. This is L plus L0. And L0 is this one, small dl by d minus d. Okay, now we have to substitute these limits. Yeah, in place of L0 we have this one. So 4WL square by pi e into capital D minus small d whole square into take minus common outside. You will have 1 by L plus L0 minus 1 by L0. Okay, or taking minus inside, you will have this one plus this one minus. Okay, it is clear. So what is 1 by L0 plus L? L0 plus L is this one. So 1 by L0 plus L, 4WL square by pi e into d minus d square into first we'll take positive. 1 by L0 is capital D minus small d by small dl minus capital D minus small d by capital dl. That is 1 by L plus L0 is this one. Okay. So in this d minus d by L is common. We can take that out. So you'll have 4WL square by pi e into d minus d square into capital D minus small d by L into 1 by small d minus 1 by cap. So here this L and 1L cancels. Here d minus d and d minus d cancels. So the remaining is delta is equal to the total extension of tapering rod 4WL by pi e into small capital D minus small d into, and inside brackets we have 1 by small d minus 1 by capital D, which is nothing but capital D minus small d by capital D small d. So this d minus d and this d minus d also cancels. So you will be left with 4WL by pi e into capital D small d. So this is the expression for the extension of tapering rod with diameters varying from capital D to small d in a length of L. In a length of L. Okay. So this is first example, the extension of tapering rod of circular cross section. Circular cross section. Now let us take another example. The second example is of rectangular section of uniform thickness. Rectangular section, tapering section of uniform thickness, width changing from small a to small b. in a length of L. Width changing from small a to small b in a length of L, and thickness being constant. Thickness being constant. So it will be seen something like this. At one end, you will have small b. Just one second. Yeah. At the other end, we have small a. I hope this will be clear now for you. Okay. Okay. The thickness is T. Here the width is A, and at the other end it is smaller width is B, which is subjected to an axial load of P, which is subjected to an axial load of P, and length of the bar is here. So here also we will be considering an elementary strip at a distance x as shown in this figure, and the origin for x is now taken at the left end where the width is maximum, width is larger width. Smaller width is b. Okay, so here the distance x from a, at this distance the width of the section, let bx b suffix x be the width of the section. So we can find bx by using again the similar triangle property only, similar triangle property. Okay, so change in width in a length of L is a minus b. Okay, so here bx is given as a minus b by L into x. A minus b by L is change in length per change in width per unit length. Change in width per unit length. And what is the change in width per for a distance x is a minus b by L into x. This is the change in width. So width is or decrease in width. Say this is the decrease in width. What is the initial width? It is a. So a minus decrease in width gives the width at section x. Width at section x. That is bx. Okay. So bx is given by this. Now we approximate this a minus b by L as k. We replace this by some constant k. So bx is now a minus kx, where k is a minus b by L, where k is a minus b by L. So what is the cross sectional area of this at a distance x? The cross sectional area of strip at distance x is width is a minus kx into thickness. Okay, so the stress on this section is P by area, that is a minus kx into t. So the stress on this section is P by load by area. Area at the distance x is a minus kx into t. Okay, and the strain, or directly we can find the extension of this elementary rod delta x as stress by Young's modulus multiplied by length of the strip, that is dx. Length of the strip that we are considering is dx. Okay. So sigma x is this one. We can replace this now. P by a minus kt or et into a minus kx. Okay. P by et into a minus kx into dx. This is the extension of the elementary strip. Stress by Young's modulus gives strain. Strain multiplied by length gives extension. So the total extension of the tapering section over a length L is given as total extension delta is given by integral of delta x, that is integral of p by et into a minus kt kx into dx between the limits 0 to L. So the limits for x here are 0 to L only. 0 to L. Because we are taking origin at left hand and this section moves from left hand to the right hand in a length of L. So the limits for x will be 0 to L only. 0 to L. Okay. So what will be the integral of this now? Yeah, delta is equal to total extension. You take the constants here, p by et out of integral sign. P by et integral of 1 by a minus kx dx. Okay. Now 1 by x dx. We have to use the formula 1 by x dx. Okay. So here in place of x we have a minus kx. Otherwise we can substitute also. You substitute a minus kx by, you replace this. Okay. You make this substitution. A minus kx is equal to t. So what will be dx now? Minus k dx is equal to dt, or dx is equal to minus dt by k. So by making these substitutions here, we get delta is equal to p by et into integral of 1 by t. Let the limits be 0 to L only, because we'll make again resubstitution for t, and minus dt by k. dt by k. So take the constant k out again. We'll have p by etk. Integral of 1 by t is log t. Okay. And now resubstitute the value of t, which is a minus kt. Okay. So p by etk into log a minus kx, and the limits for x are 0 to 1. So with this now, p by etk will be getting log in place of k also we have to make substitution. What is that k value? K value is a minus b by L. Okay. So we have a minus of a minus b by L into, in place of x we will substitute L. So this gives log of a minus of a minus b, that is b. Okay, minus log a, because substituting the lower limit you will have log a here. So p by etk into log b minus log a. This is delta. Okay, in place of k we will replace again a minus b by l, so it becomes pl by et into a minus b into log of b by a. Okay, this is the expression for extension of tapering rod with rectangular cross section, thickness being constant and width varying from uh, at the larger end the width being small a, and at the smaller end the width being small b. So the extension of the beam is given by this expression PL by ET A minus B into log B by log A. Okay, that is all for today's class. Thank you. We will discuss some more topics in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.